Hello, and welcome to the Probability, Normal Distribution, and Z-Scores lecture. It's a big one today, so strap in. So we are going to discuss how probability is related to statistics in terms of using normal distributions and Z-scores. So we're going to start off fairly simple with probability, stuff you guys are already familiar with, I'm sure. And then we're going to start talking about how that relates to statistics and a little bit of inferential tests. So probability, here we go. So like I said, probability is something you guys are probably familiar with. Me just saying probably is actually a probability. Anywho, so there are different options or different ways to think about probability. You can say like, oh, what are the chances it'll rain today? Oh, there's a 75% chance of rain, or 0 if you live in the Central Valley, apparently. How likely is a plane crash? How likely are you to be in a fatal car crash? Hopefully 0, but there's always a small chance, not to, be Debbie Downer on this mofo. And anyway, probability is something that we deal with on a regular basis. And we use that term we use it really colloquially when we talk about, oh, what's the chances it'll rain today? So with probability, we can think about it in terms of percentages, like, oh, there's a 35% chance of rain or a 30% chance of rain. But keep in mind that percentages can be converted to decimals, which can be converted to fractions. So a 30% chance of rain would also be 3/10, and it would also be 0.30. All of that is saying the same thing in terms of probability. It's at 30% or 3/10 or 0.3. Sorry. Anyway, hold on. There was a weird thing that just happened. Let me just kind of get back to that. Okay, so all of that is saying the same thing. Now, to calculate probability, there's, of course, a formula for it, and it looks more complicated than it really is, or at least it looks more complicated, but we pretty much are likely familiar, or at least can figure out how to calculate probability. So this equation translates into the probability of an outcome, which is represented by P of X equals the number of times, or the frequency of the outcome, so F of X, divided by all possible outcomes, which is known as the sample space. So to find the probability of an outcome, you're taking the total number of times the outcome can occur and dividing it by the sample space. So, for instance, if you think about, oh, what's the probability that you'll roll an even number with a regular 6-sided die? Think how often it occurs that you would roll an even number. Well, there's 2, 4, and 6. So that's 3 times out of 6 that you can roll an even number. So again, the 6 represents the sample space, which is the total number of possible outcomes. That's the even and the odd numbers on the 6-sided die, 1, 2, 3, 4, 5, 6. And so the probability, again, is taken by taking the frequency of how often that event can occur. So the frequency, how often you can get an even number, which is 3 for 2, 4, 6, and dividing it by the total number of possible outcomes, which is 6 for 1, 2, 3, 4, 5, 6, all the different numbers on that 6-sided die. So your probability of rolling an even number is 3/6, or 0.5, or 50%. Fairly simple, fairly straightforward. There are some rules to probability. So one is that probability varies between 0 and 1. Since we're using fractions and decimals and percentages to represent probability, there is never going to be an outcome where you have less than a 0% chance or greater than 100% chance of something happening. We do say like, oh, there's a 110% chance that it's already raining. But that's that's more used colloquially. Statistically, it's not really going to work in terms of probability. You can say things like, oh, profits increased by 250%, but that is not an issue of probability. That is something completely different. So when we're talking about probability, it can only be between 0 and 1. Or between 0 and 100%. So you can't say, oh, I have a negative 5% chance of winning the lottery. That doesn't make sense. How could you have less than 0% chance? If it's not going to happen, it's not going to happen. You don't have to, slap me in the face and say I have negative probability. Not to mention, it just doesn't make sense. And then for the probability of being greater than 100%, well, how can it, if you have a six-sided die and I'm trying to see, oh, how likely is it that you're going to roll a number 1 through 6? So 100% chance you're definitely going to roll a number between 1 and 6 if you have a six-sided die. But I say, oh, you have 110% chance or 120% chance of rolling a 1 to 6 number. It's like, no, there's just 100% chance. I can't have a greater chance if it's just 100. It's gonna happen. There is no such thing as greater than 100% chance, again, when it comes to probability. Probability also can never be negative. So I mentioned this before, how you can't have a negative 5% chance of winning the lottery. Either it has the chance of happening of being more than 0, or that it isn't going to happen. That's the probability. That's just straight up 0. Variability also kind of follows the same suit. So whereas probability can never be negative, neither can standard deviation, or neither can variability. You can have a standard deviation of 0, but you can't have a standard deviation of -5. It's just 0 is they're all the same. Now, when we talk about the empirical rule, how I said, oh, you subtract a standard deviation and you add a standard deviation, keep in mind that's not necessarily stating that your standard deviation is negative. You're just subtracting your standard deviation of 5 or 7 or whatever your standard deviation is from the mean. And that's just for us to provide a frame of where 68% of the data lie, 95, and 99.7. To do that, we have to subtract the standard deviation, but that is still, you still have a positive standard deviation, but you're just subtracting that from the mean to get the width of, okay, so from 68%, it's going to be from 5 to 10. 68% of the data is between 5 and 10. 95% of the data is between 15 and 25, or what have. Okay, that was totally wrong, but you understand. So why is it that we're learning probability in a statistics class? Why does this matter? This seems like simple stuff that you might have learned in like algebra or algebra 2. I don't remember when you learned about probability, but either way, why are we talking about it now? Well, it's key to figuring out how likely an event or a behavior is to occur. Remember, this is a psychology class. This is Psych 42, Introduction to Statistics. So what we do in psychology is we kind of tend to focus on things that humans do and the likelihood that it happens. Probability is key to do this. It's also key when understanding inferential statistics. Now we're not going to really get into hardcore inferential statistics quite yet. Like I said, that's more so after the first exam. We're going to start getting into the different types of inferential statistics. But keep in mind that probability is a factor in every single one. So most behavior is normally distributed. That could be, behaviors ranging from, how people score on a depression inventory, an anxiety inventory, how often people pop their gum while they chew it. Every behavior can be normally distributed. And with a normal distribution, it follows the empirical rule. Keep in mind that that is at 68% of all the data in a distribution lie between 1 standard deviation above and 1 standard deviation below the mean. 95% lie between 2 standard deviations above and below the mean, and 99.7% of the data falls between 3 standard deviations above and 3 standard deviations below the mean. So with that being said, we can use the empirical rule to determine the probability of obtaining a particular outcome or behavior in research. Since all behavior, or at least most behavior, is normally distributed, the empirical rule uses a normal distribution. We can put those two together and say, hey, we can find the probability that this person has a behavior that is outside the norm. Maybe it's above 2 standard deviations from the mean or below 2 standard deviations from the mean. That's a little abnormal. But anywho, so I mentioned how most behavior is normally distributed. So let's talk about normal distributions for a bit. There are several different characteristics. You're not going to be asked to memorize all of these, just a few, and I'll let you know which ones are, like, well, not most important, but you know what I will be testing on. So first off, the normal distribution is mathematically defined. It has a formula. Don't bother memorizing it. It's a waste of time if you're just doing this intro to stats class. Maybe if you get into like mathematical theory, sure, but we're not doing that. So pretty much all data follows the normal distribution roughly. It's never going to be exact, but it's close enough oftentimes that in statistics, we're just like, yeah, sure, let's roll with it. Close enough to the normal distribution. The normal distribution, number 2, is theoretical. Since no behavior or no data set really follows the normal distribution formula exactly, because it's theoretical. It's like in a perfect world it would, but of course we're not in a perfect world. I mean, for God's sakes, we're on this class online because we don't know how to wear masks in America. But anyway, it's close enough. It's all, our data sets are generally a close enough approximation to the normal distribution that we, again, roll with it. The third, this is something that's important. These 2 points here on this slide are important that I want you guys to know about normal distributions. The mean, median, and mode, so again, those are the 3 measures of central tendency we've discussed in this class, are all located at the 50th percentile, meaning it's right in the middle. The mean, the median, the mode, they're all smack dab in the middle. It's perfect. And with it all being perfectly in the middle, that is saying that the normal distribution is symmetrical. So if we were to fold it in half, it would be perfect. Now, just so you know, I'm talking about normal distributions. I'm talking about, oh, they're symmetrical. Oh, they're this. Oh, they're mathematically defined. Oh, but they're theoretical. Oh, well, to let you guys know what the hell it is I'm talking about, I'm sure you guys are familiar with at least the look of a normal distribution. That is a normal distribution. Keep in mind that my, if you can think of it as the standard bell curve, like I said, though, in statistics, we refer to it as the normal distribution. My drawings aren't going to be perfect. They're not going to be symmetrical, but, you know, just, yeah, use your imagination. So the mean, median, and mode all follow that dotted line right in the center. All of those 3 measures of central tendency meaning in the center, are located right in the center. Again, it's a perfect world where this rarely, if ever, happens with actual data sets that you have. But again, we approximate in statistics, behavior is relatively close enough to a normal distribution that we roll with this. So the mean, median, and mode are all in the center. If we were to take our normal distribution and fold it in half on that dotted line, not my normal distribution, because like I said, I cannot draw symmetrically. But if we were to take the normal distribution and fold it right in half, right at that mean, median, and mode line, it would be perfectly lined up. It would be symmetrical. So normal distributions, the mean can be any value. So keep in mind, we use normal distributions to discuss behaviors or tendencies or anything that we can measure in psychology. So it can be any value. If you have a depression questionnaire and you are, let's say it's 20 questions and it's all on each question's on a 1 to 5 scale, where the higher you score on this depression questionnaire, the more depressed you are. And the lower you score on it, the less depressed you are. Well, if there's 20 questions and there's 5, it's a 1 to 5 Likert scale for each question. Let's say to get your depression score, you just add up all your responses. And again, the higher you, the closer to, let's see, 20 times 5, the closer to 100 you score, that would be well, I guess I'd say perfect score on a depression inventory. If you score 100 on this depression inventory, again, 20 questions, 5 a 1 to 5 Likert scale each. So if you answer 5 on every single one and you add up all your scores, your depression score would be 100. Now that's probably not going to be the mean for, that's not going to be the mean, because that's saying most people have said, yes, I have a very high depression level of 100. Let's say that the mean for that is like, I don't know, 35 out of 100. So 35 is the mean depression score. You're going to have some people hovering around 35. You're going to have some people that are lower, some people that are higher, like that 100 person. So that is just one normal distribution of a depression inventory where the score was 35. Now I can give a different depression inventory, and maybe this one has 10 questions and still 1 to 5 Likert scale. So now the highest score you can get is 50. Well, the mean for that one, if we were to give that to a bunch of people, maybe the mean for that score or for that inventory would be, I don't know, 15. We have different means. So when I say the mean can equal any value, it's just thinking about all the different types of behaviors there are, or all the different types of ways we can collect data. And the mean can be anything based on what you're looking at. So just looking at 2 different examples of a depression inventory, we had 2 completely different means. But both can use the normal distribution. Both are applying the normal distribution in order to calculate some inferential statistics. I can take the average weight loss in the class over the last month, let's say, and like I've lost 2 pounds. Oh, I've gained 2 pounds. I've stayed the same. I've lost 50. I've gained 50. What have you? But I can take the mean of everyone's, total weight loss or possible gain, and I can find the mean for that. And it's probably not going to be 15 like it's going to be for our depression inventory, or 35 like I did for the first depression inventory. So when I say the mean can equal any value, what I'm saying is that all the different things that we look at in statistics or in psychology, there's tons of them, and they're going to have different means because they're just looking at different things. They use different scales. They're looking at just a variety of different things, to where, yeah, you're going to have a mean equal to any value, because hell, our data is oftentimes it's not necessarily one number set that it follows. So with that being said, the mean can equal any value, and the standard deviation can equal any positive value. Now keep in mind, we can never have a negative standard deviation or a negative measure of variability. It's either they're all the same or they're not. But with normal distributions, they're not all the same. With normal distributions, you don't really have a standard deviation of 0, because then that would just be represented by a straight line. Everything is right here. We don't have any variability. If we were to draw it on a graph, if you had no variability, then everything would just be in a stick. So like I said, we can't have a negative standard deviation, so every standard deviation has to be positive. So this is going to be important when we talk about z-scores, which we will today. So characteristics, again, the 7th characteristic is the total area under the curve of a normal distribution is equal to 1.0. So you see here that we have the 68, there's a reason why we have the 68, 95, 99.7 rule. Now we kind of round it off, 68.26, 95.44, and 99.72. But we pretty much round it to be the empirical rule to be 68, 95, 99.7. But you'll see that here's our mean here, and here's one standard deviation above. Again, this is in population. You can tell because we're using mu and sigma to represent mean and standard deviation respectively. But from our mean to one standard deviation above, there's 30.3413. That is the area of this area right here, the area of the area. So that's how much space we got between one standard deviation above the mean, 0.3413. What that is telling us is that this represents 34% of the distribution here, because again, it's on a 0 to 1 scale. We have 0.214, 0.13, 0.0214, 0.1359, 0.3413, etc. And it's symmetrical, so it's the same on both sides. But if we add this up, and there's a little, if we add all this up, it would equal a little less than 1.0. That's because it's representative of 99.72% of the data. So you have stuff this way and you have stuff that way. But a vast majority is between 3 standard deviations above and below the mean. This is where most of the data lies. So when we have a total area of equal to 1 underneath this line of the normal distribution, underneath this curve is equal to 1, we can see that, oh, from, 1 standard deviation above the mean, it's 0.3413. And if we add these two together, 0.3413 times 2, that's 68.26% or 0.6826. Either way, that is representative of the total area of the under the curve is equal to 1. All right. So the next characteristic is that the tails of the normal distribution are asymptotic, meaning that they never quite touch the x-axis. So looking back at this here, you see this is floating. This, we have the line here of the normal distribution, and it's just floating above this x-axis. It never actually touches it. So now you can, tell your friends, ooh, normal distributions are asymptotic, and they'll probably think they're swearing at you, but, whatever. So normal distributions could be an infinite number of possibilities because we have an infinite number of things that we can measure in statistics, depression inventories, anxiety scores, how often you chew your gum, how many animals you have, etc. So in order for us to kind of make it normal, or not so much normal, we're not normal except for our distributions. But in order to find the probability of a score in, let's say, what's the probability of someone scoring a 15 on our depression inventory where our mean was 35, we would have to convert that. There would be an infinite number of different ways to convert probabilities from my 35 mean depression inventory to my 15 mean depression inventory. If we didn't have a way to bridge the gap, we'd have to have a separate way to do it with a mean of 15 and 16 and 17 and 18 and 19 and 20, and then all the different standard deviation combinations we have. It can be a little overwhelming. So what if there's an easier way? There has to be an easier way, and we'll get into that with z-scores. But before I talk about z-scores, because that is a way to make all of these infinite numbers of possibilities for normal distributions more manageable, and we can convert them to a standard normal score. Let's think about it in terms of going shopping or getting new clothes. So let's say that you need to get new shirts for, I'd say class, but like, if you wear pajamas, you wear pajamas. But anyway, when it comes to shopping, let's say you go to a store and you try on shirts, and at Kohl's, let's say you are a size M or a medium. Then you go to a different store. Maybe you go to Walmart or Target or Forever 21 or wherever the hell you shop for your clothes. I don't know. And there you are actually a large. So you're a medium at Kohl's, but a large at Forever 21. And so it's like, oh God, I can't just go to a store and find, oh, I'm a medium, so boom, I know, I don't even have to try it on. I know this is going to fit me exactly. No, we have to try on clothes to make sure that they fit. So this happens so often, and it's so freaking irritating to me, but whatever, what are you going to do? So when we think about how, hey, I'm a medium at this store, I'm a large at this store, maybe I'm an extra small at this store, at a XXX at this store, or whatever. We have all these different sizes that one person is, that it's kind of hard to think like, oh God, why can't there just be one size or one agreed upon measurement for clothes where if I grab a medium at this store, it's going to be the same as the medium at a different store, which is what these standardized clothing size could be. I wish this would happen. If any of you guys can like fashion or something, please try to make this happen. Although I realize it probably won't, because we all have very different unique body shapes and sizes. So Maybe it's just because I'm lazy and I hate trying on clothes. It definitely is because I'm lazy and I hate trying on clothes. But anyway, so instead of trying, if we had this normalized clothing size, instead of having to try on different sizes at the store, oh, I'm a medium at Kohl's, I'm a large at Forever 21, I'm a small at Target or whatever, instead of having to go through this rigmarole of all this extra work of, okay, well, I'm different here, I'm different there, I'm this there, I'm that there. The standardized clothing size is just, if you're a small or a large or a medium or what have you, that will apply to everywhere you go. So long as they have a little thing on on their window that says we carry standardized normal clothing size or standardized clothing size, you know, oh, I know I'm a medium in the standardized standardized clothing size. So boom, I know I can shop here. They have that little notification on their door, that little sign on the door saying, yep, we carry these sizes. So I can grab a medium. I don't have to worry about it. Now, obviously, life doesn't work that way. Fashion doesn't work that way. But the standard normal distribution works the same way. It converts any normal distribution, be it, you know, your mean of 15 for your depression inventory and a standard deviation of 5, I don't know, or the mean of 35 for the other depression inventory with a standard deviation of 12, or the mean of 7 for, I don't know, number of animals you own, or whatever, I don't know. All the different possibilities of behavior that is normally distributed, we can convert into a z-score to calculate the probability of having a particular score on the depression inventory, or having a particular number of animals, or whatever that behavior distribution is looking at. So the standard normal distribution, each different individual behavior or outcome that we're looking at, that can be representative as, oh, I'm a medium at Kohl's, but I'm a large at Target, and I'm a small at Walmart or whatever. All these different things can be converted to z-scores, or all these different sizes can be converted to the standard normal clothing size, and we can, you know, find our size or find the probability without having to go to all these extra steps of converting for individual normal distributions, like for individual behaviors, or we don't have to try on all these different clothes when we go to Kohl's or to Target or what have you. So the standard normal distribution, or the Z distribution, it has a mean of 0 and a standard deviation of 1. So if we were to draw it out, it would have 0 be the middle, and then 1 standard deviation above, 2 and 3, and the negative 1, 2, and 3 represent just 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. So when you get a z-score, and we'll be calculating z-scores, that value represents the standard deviations away from the mean that that score is. So if we were to calculate, you know, there's an equation to calculate your z-score, and we got negative 2.5, that would be about right there. That's saying that it is 2.5 standard deviations below the mean. So here we have a z-table. I do have a module entitled Tables on Canvas, and a z-table is there. So you can print it out if that helps you. I would suggest printing it out just so you don't have to keep scrolling through it, because I think it's about 4 pages. So you can just print that back to back if you have those capabilities. But if you don't have a printer, that's fine. You can still obviously use the PDF on Canvas. It's not going to hurt you. But this is just a small excerpt of a z-table. So I'll show you guys how to read it, and I kind of have an explanation here. But the A column, the first column that says Z, this column represents, okay, so we calculated our Z-score and we got 0.96. So you would look for 0.96 in your Z-table, and there you go. And then the columns B and C, this is column C, those represent, okay, so what is it the question is asking you? Which probability are you looking for? But what this is saying, okay, let's stick with 0.96 here. Oh, I can't select it. But anyway, let's stick with 0.96. The area between a z-score of 0.96 and the mean is 0.3315. The area from 0.96 to the end of the tail, so not coming inward towards the mean, but going outward towards the asymptotic tail, that is 0.1685. So just as a little visual of that. So let's say we have a z-score of just straight up 1. So that's 1 standard deviation above the mean. What that's saying, when we look at the table, is that the table says that the area between z and the mean, which is in column B, is 0.3413. So we have 0.3413 at a z-score of 1. So it's saying that from here, from the mean to the first standard deviation, or to a z-score of 1, keep in mind that z-scores represent standard deviations above or below the mean. So we have a z-score of 1, that's saying it's 1 standard deviation above the mean. The area from mean to our z-score of 1 is 0.3413. Okay, and the area, so it's this red circled area here. That's all we're looking at in column B. When we have a column C, it's the area beyond Z. So here's our z-score of 1. Column B is the red area. Column C is looking at the purple area and pretty much extends all the way out. So when you add these two numbers together, it equals 0.1573, but the Z table states it's 0.1587. The reason why there's that little disparity is because it's also, in the Z table, it's accounting for the tail that is asymptotic, that is not covered here. So it's this area and beyond. To infinity and beyond. To the tail and beyond. Yeah, sure. Anyway. So the Z transformation. Now I told you there was going to be equations. It's not too difficult. You'll notice that we have two equations here. One is representative of a sample and the other is representative of a population. Guess which is which? That's right. The one that has the mu and sigma represent the population. So this here, that's the population. This here is representative sample. But essentially, this is our Z transformation. This is how we get Z scores. Now, X represents the value that we're looking for, the value that we want to convert the Z score for. So I have a large. What does this convert to in my standard normal clothing size? You know, what is a large at a Kohl's? How does that translate to the standard normal clothing size? What is that? And then the mu, or the M, is the mean for population and sample respectively. And you divide it by the standard deviation. Again, sigma for the population standard deviation, or just, like I said in the previous video, I will represent sample standard deviation by just SD. But if you're more comfortable with a lowercase s, feel free to use that. But I'm still talking about standard deviation. All right. So let's kind of do a quick little example. So a researcher measured the farthest distance in feet that students move from a podium during a presentation. See, this is just one of the many things that we can have a normal distribution for. I talked about depression scores. I talked about number of times you pop your gum, number of pets you have. Here's another one. The furthest distance, or the distance in feet that students walk away from a podium as they're presenting. Random. But anyway, so the data were normally distributed with a mean of 12 and a standard deviation of 2. What is the z-score for 14 feet, or x equals 14? So when we're asking for z-scores, that 14 is what's representative of x. So keep in mind that our formula was x minus mean divided by standard deviation. So we'll plug that in. X of 14 minus the mean of 12, as it's represented here, divided by 2, which is our standard deviation, as it says right there. 14 minus 12 is 2, divided by 2 is equal to 1. So our z-score for 14 feet in this distribution is going to be 1. Our z is equal to 1. Okay, that wasn't too bad. Now, using the same example of, oh, how far do, the length of the distance traveled in feet from a podium as students present, Now let's start using the Z table for that. So we got our Z score of 1 of our mean of 14 minus our score of 14, the number of feet they travel from the podium of 14 minus our mean of 12, I misspoke there, and divided by the standard deviation of 2. That gave us our Z score of 1. So here's where we start needing to understand what the question is asking us so we know which column in the table to use. So the probability, what is the probability of students straying more than 14 feet from the podium? Just to make this a little easier, let's kind of draw this out. So let's say we have our mean of 12, right, for this equation, or for, not this equation, for this distribution, a mean of 12 and our standard deviation of 2. So let's kind of draw out the lines for where all these things are. I've labeled all the standard deviations above and below the mean. So you'll see that the center line is 12, that's our mean. And since our standard deviation was 2, I added 2 to get 14, 16, and 18 to get 1, 2, 3 standard deviations above the mean. And I subtracted 2 to get 10, 8, 6, or 1, 2, 3 standard deviations below the mean. Okay, so that's what that looks like so far, if we were to draw it out. Now this question is asking for what is the probability of students straying more than 14 feet from the podium? Oops, that was very crooked. Okay, so there's 14. And we want to know the probability of students straying more than 14 feet from the podium. So I'm just shading poorly, shading the region of the normal distribution that I want to know in regards to this question. Again, all I did was I took, keep in mind, that the question stated our mean of 12 and our standard deviation of 2. So that's how I was able to draw this graph. Similar to the empirical rule, I took that 12, put that in the middle, and I just subtracted 2, subtracted 2, subtracted 2 to get this direction of the distribution. Added 2, added 2, added 2 to get that direction of the normal distribution. So if you're wondering how I got those numbers, that's how I got it. And I shaded the region that I wanted to find the probability for, just to kind of keep it, you know, in my head, to make it easier. I find it might be helpful for you guys to also do the same thing if you're having trouble understanding, okay, which column do I use, dude? I suggest you draw it out for yourself before you continue. Okay, so we've already converted that score. For a score of 14, we have a Z score of 1. So now we look at the table, the Z table, and we want to get the probability of students scoring above that. Again, since I've shaded it here, above 14, above 14. So when we're asking for that, when we have that, we're looking for the area beyond Z in the table, or column C. So the area between me and Z, column B, that would represent this area between the dotted lines. Column B on this equation represents right there, the part I have not shaded, the part that I don't really care about for this particular question. Column C is representative of from Z to the tail. Oh, from Z to the tail. So that's the shaded region that we want. So the probability of students straying more than 14 feet from the podium is 0.1587, or you can round that to 16% if you're so inclined. But essentially, the probability of students straying more than 14 feet from the podium is 0.1587, as it states in our Z table. Okay, cool, nifty, bitchin'. We got that taken care of. Now let's look at some other equations or some other examples. So we have a researcher measures the number of minutes employees spend in off-task activities. The average is 5.2 minutes with a standard deviation of 1.6. What's the probability of employees that spend less than 6 minutes off task? Okay, so here are some different examples of how to use z-tables and how they can work. You'll notice the table is drawn out here, so I don't have to draw it on my board again, and I'm currently erasing my board poorly, but okay. So what we're gonna do is we're gonna draw out that again. We're gonna draw out the distribution, just like I did for the straying from the podium, except, well, one, the book already drew it out for you, but either way. We have our mean of 5.2, so that's in the center, and then we're adding 1.6 to get, okay, 5.2 plus 1.6 is 6.8, plus 1.6 is 8.4, plus 1.6 is 10, 5.2 minus 1.6 is 3.6, minus 1.6 is 2.0, and then minus, yet again, is 0.4. So I've drawn out the normal distribution with 3 standard deviations above and below the mean of 5.2 minutes. Now, this question is asking, what's the probability of employees that spend less than 6 minutes off task? Well, here's 6. We're just going to put it right there. So there's 6, if we want to draw that. And we're shading this region. We want to know of the probability of employees spending less than 6 minutes. So that's going to be in this direction. So we calculate our z-score and we get, we take our 6, which is representative of our x. That's what we're trying to find the probability for. So we take our 6 minus 5.2, which is our mean, and divided by our standard deviation of 1.6. So we get a z-score of 0.50. Now, when you look at your z-table, you're looking at column B. You're looking at column B, which is stating 0.1915. Now, why are we looking at column B? I'm trying to find out all this information. Well, column C would get us this information from 6 to the end of the tail. But you'll notice that that's not the area that we're shading. So while we have when we look at proportion or at column B, it tells us 0.1915. We're not done yet though. Keep in mind, we want to know everything less than 6, and that only tells us from 5.2 to 6. So the probability of scoring between 5.2 and 6, or the probability of spending 5.2 minutes and 6 minutes off task is 0.1915. Cool, but that's not what we're looking for. We want to know what's the probability of spending less than 6 minutes off task. So that's not only this, but less than 5.2 as well. So to do that, we would just have a little adding match, or we would just add. So we have the probability from 5.2 to 6, but we also want to know everything else in between. Now, you are going to add 0.5 to that 0.1915. in order to get the probability of spending less than 6 minutes off task. Now, why are we adding 0.5? How do we know it's 0.5? Where did you just pull this number out of your ass from, Professor Cooper? Well, keep in mind, when we talked about, there's 2 things that we've talked about in terms of characteristics of normal distributions. One is that the total area underneath the curve is equal to 1. 2, actually there's 3 things. 2 is that the mean is in the mean, median, and mode, or in the very center. And 3, they're symmetrical. So if it's at the very center and it's equal to 1 and it's symmetrical, that means when we split this down the middle, over here is 0.5 and over here on this side of the mean is 0.5. That's the area that's to the left of the mean, and the area to the right of the mean is 0.5. So we already have the probability of between our x and our mean of 0.1915, but now we have to add the rest of the distribution to that. So we just take 0.5 plus 0.1915, and that gives us a probability of 0.6915 as the probability that people will spend less than 6 minutes off task. So why I mentioned that you might want to draw your graph is because you don't want to get these confused. No, no, go. I am working. I have told you multiple times I am working. So with that, oh, now I'm a shitty person. Okay. So with that being said, I find it easy to draw your graphs so then you know exactly what it is you're looking for. Because if you don't draw your graphs and you just focus on the Z table, you might get confused. So when you draw it out like this, it'll be easier for you guys to keep it, you know, keep it intact. So that's part of the magic of symmetry. But so when you have to find scores below the mean, remember the standard distribution is normal. So when you find, if you have a negative 0.92, like I have here, that is gonna have, you're gonna look for 0.92 in your Z table, and the distance between 0.92 below the mean and 0.92 above the mean, that's gonna be the same distance. It's gonna be 0.1788 both times. Finally, what I want to go over is locating proportions between values. So let's look at this question. Students who chewed gum when taking a test for a second time scored on average 20 points higher with a standard deviation of 9. What's the probability that a student who chews gum will score 11 to 29 points higher? So we have two X's here. We want to know the probability of 11 and the probability of 29. But what we want to know is the distance between them. So first off, let us draw out this distribution. Let's figure out exactly what we're doing here. So it says that our average, our mean is 20. So that's going to be in the middle. And our standard deviation is 9. So 29, 38, 47, 11, 2, -7. Okay. So I've drawn out the distribution of what this looks like. Again, it told me that the mean is 20. So I put that in the center, and the standard deviation was 9. So I added 9, added 9, added 9 to get 1, 2, 3 standard deviations above the mean, subtracted 9, subtracted 9, subtracted 9 to get 1, 2, 3 standard deviations below the mean. Okay, so we want to know the probability of a student who chews gum will score between 11 and 29 points higher. So it's not pretty. Like I said, my shading is not going to be great, but I've marked it here of 11 and 29, and I just shaded that this region here between these two numbers is what we're looking for. Okay, so when we're finding these proportions, we're going to calculate two z-scores. Whenever it says, what's the probability that a student who chews gum will score 11 to 29 points higher, or what's the probability that so-and-so will score between X and Y, you're going to be looking at two z-scores. You're going to be calculating it 2 times. So the first one, let's just start with 11. 11 minus 20, again, the 11 that I'm getting from here. 11 minus our mean divided by standard deviation. -9 divided by 9 is equal to -1. You'll find that the proportion for 1 or -1, since it's symmetrical and they're going to be the same, in column B, since we're looking from our score to the middle, if this were shaded, we would be looking at column C, but we're not. This between here and here is shaded, so this is column B. So the proportion in column B states it's 0.3413. We do the same thing for the other score, so 29. 29 minus 20 divided by 9 is equal to 1. So hey, The proportion of z to the mean is the same for -1 as it is for 1. It's 0.3413. You add them together, and it's 0.6826. We're adding them because we need to add this, because so far with one z-score calculated, we're only getting from here to here, and with the other one, we got from here to here. But we need to add those two together since we want to find the probability from here, from 11 to 29. So adding both of these together, and that is 0.6826. That is the probability. So at this point, now let's practice calculating z-scores. Oh my God. Hold on a moment. Okay, so let's do these practice problems. So we have a mean of 26 and a standard deviation of 6. What's the probability of scoring above 10? Well, you guys can feel free to do this with me. Okay, so we have a mean of 26, so I'm going to mark that in the middle. Again, I'm drawing the normal distribution just to know exactly what it is I'm looking for. And a standard deviation of 6. So 1, 2, 3 above, 1, 2, 3 below, and we're going to start doing that. Okay. So I've drawn out the distribution. So okay. So boom, I've drawn it out with 3 standard deviations below and above the mean. Now we want to know the probability of scoring above 10. So I'm going to find 10 on my distribution here, which is about right there. About right there. I drew it kind of small. But we want to know the probability of scoring above 10. So from that line I've drawn, we want to know that much. There's only this little small gap here that's not covered. But you'll see that from 10 up, that's what we're looking for. Okay, so now that we have that, let's find our z-score. Now that we know exactly what we're going to do. So 10, our score of x, minus 26, our mean, divided by 6, which is our standard deviation. That is going to be -16 divided by 6, which, truth be told, I'm not going to do in my head. That's why we have calculators. So that gives me a z-score of -2.67. I'm rounding it again to the nearest hundredths place. Oh, it's -2.67, by the way. So now what I'm going to do is I am going to look in my z-table. Now I have a z-table ready to go, but I have to show it to you so you guys can, actually see the damn thing. So this is what your z-table looks like. Now our z-score was -2.67. This table doesn't have negatives, but since it's symmetrical, we're just going to go to 2.67. Here we go. Here we go. Right there. Now we're looking, oh God, okay. Now we're looking for, which column are we looking for? Are we looking for the area between mean and z? Keep in mind on here, between me and z would be between 10 and 26. Or are we looking for column C, the area beyond z in the tail, which on this side would be from 10 down below. So from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So 10 below, it would be representing column C. Well, we don't want that. Obviously, we want column B. That's the part that's shaded from 10 to 26, or from our z to the mean. Our z of 10 to our mean of 26. That's what we're looking for. So, all right, let's go back down to 2.67. Column B is right here. So we have 0.67 0.4962. So we have from here to here, we have this part so far. Well, we want to get the rest of it. What do? Why? We add 0.5. Because again, it's all the area from the right of the mean. So the entire right side of the mean on this graph is 0.5. So 0.5 plus 0.4962 equals okay. So the probability, let's go back to the PowerPoint now. The probability of scoring above 10, so most of it, is 0.9962. Because I took the column B, which was from 10 to 26, and then I added 0.5, which is everything from 26 up, to get the total shaded area. So the probability of scoring above 10 is 0.9962, which makes sense since the area underneath a distribution is equal to 1, and most of this thing is shaded. It makes sense that the probability is 0.9962, which is pretty close to 1. So, I'm gonna use this. Why am I not using a rag anyway? Alrighty, here we go. Let's do the next one. So a mean of 52 and a standard deviation of 14. Before I even get anything started, I'm just going to draw that. So our mean is 52, so I'm going to make that in the middle, 52, and then 14, 52. I'm just going to check myself because I don't want to wreck myself. Okay, so I've drawn that out. What is the probability of scoring between 30 and 60? 30 is about right there. 60 is about right there. Sure, it's not pretty. Okay, now I've already shaded it, but I'll show you. Again, I've drawn out where it is. So I've drawn out my normal distribution with the mean of 52 being right there. And we want to know the probability of scoring between 30 and 60. Okay. So since this is looking for the probability between X and Y, I know that I'm going to be calculating 2 z-scores. Doesn't really matter which one you start with. I'll just start with 30. So 30 minus our mean of 52 divided by our standard deviation of 14. 30 minus 52 divided by 14. That equals negative 1.57. And then let's look for the other z-score before I go to the z table. So 60 minus 52 divided by 14. So 60. So 8 divided by 14 is 0.57. Okay. So we have 2 z-scores for our 2 numbers. The z-score of 30 and the z-score of 60. Our z-score of 30 is negative 1.57. The z-score of 60 is 0.57. Okay, so now let's go to the Z table. Let's go back to that. All right, so 1.57, and we are looking for column B because again, it's inward to the mean. So for column B, I'm starting with our Z-score for 30, which was negative 1.57, but it's from here, our 30 is right there, to here, our 52, our mean. So it's between here and here. That's what this is telling us right now. The Z-score I'm going to get right now, the proportion in column B is that area. So 1.57, 0.4418, right here, 1.57, column B, since it's towards the mean, 0.4418. And then our Z-score for 60 was 0.57. Oh, look, here we go. Right there, 0.2157. Now, in order to find the probability of scoring between a 30 and a 60, what we're going to do is just add the two column B proportions that we found. So again, for our Z-score of negative 1.57, that proportion we found in the Z table was 0.4418, and we add that to the proportion we found for our Z-score of 60, which was 0.57. So we're adding 0.2157. So the probability that they're going to score between 30 and 60, let's go back to this. The probability of scoring between 30 and 60 is 0.6575. Proportion B, or column B, we added these two together. That gives us 6575. Lastly, we're going to do the last one, if you haven't already, or if you're following along with me. Cool. Welcome. Hello. Nice to see you. Well, I don't see you. But anyway, our mean of 30. Again, I'm drawing out the distribution before I start anything. So the mean is 30, so that's going to be in the very center. The standard deviation of 4, 34, 38, 42, 26, 22, and 18. What's the probability of scoring below 16? Ooh, that's gonna be tiny. Okay, so I've drawn out my distribution, 30, and then I added 4, added 4, added 4, subtracted 4, subtracted 4, subtracted 4 to lay it out. And then I'm finding the score below 16. There's 16 at the very end. I'm going to shade just that tiny little space right there, since that's what we're looking for. So here we go. Just that tiny little space. So when we calculate this, we know it's going to be a very small number, considering how little of the graph we have shaded, or how little of the distribution we have shaded. But let's still calculate it. So we're going to do 16 minus 30 divided by 4. And again, this is the equation to find our Z-scores. So the X is representative of, oh, what's the probability that you're looking for? Well, we're looking for below 16. So X would be 16 minus our mean of 30 divided by our standard deviation of 4. So let's just do that right quick. 16 minus 30 divided by 4 equals negative 3.5. All right, cool. Well, now let's go to the Z table. So let's go on back. Z table, boom, bam. Let's find, again, since it's symmetrical, we don't have to find negative. We can just find 3. There we go. 3.5, 0. Now we're looking for, are we looking for column B or are we looking for column C? Column B represents from the z-score to the mean. Column C represents from the z-score to the tail. Looks like we're going to the tail. Looks like we're going not towards the mean, but we're running away from it. Column C is what we need to find this area here. And like I said, it gonna be tiny because that's a tiny proportion of the distribution that I've shaded. So let's see, where are we? 3.5, this is column C, 0.0002. So the probability of scoring less than 16 is going to be 0.0002. Wow. Now you'll notice on this Z table that it stops at 4. And it starts to kind of skip numbers too. Once you get to 0.25, you'll see it skips to 3. Once you get to a Z-score of 3.25, it skips to 3.3, skips to 3.5, 3.35, 3.4, 3.45, 3.5. Keep that in mind. But notice how these numbers are barely changing the higher and higher that you go. So that is our probability, normal distribution, and z-scores lecture. If you have any questions or if you struggled with any part of that, if you need, like, I don't understand it, let me know. Come to my office hours, send me an email or a message through Canvas, and I will definitely talk to you about it. But I hope this video is helpful to you or was helpful to you. Always feel free to, you know, follow along with the PowerPoints, although I say that now that the video's done, but you know, don't hesitate to watch this over again, rewind to certain parts if you need to see it, pause it when I'm showing the graphs or the whiteboard and everything so you guys don't miss anything. I encourage you to take notes. It'll be easier for you to keep track of and for you to understand as we move further on. But for now, that's all I got for you. If you have questions, be sure to contact me or visit my office hours. But that's all. So like and subscribe, baby.